So welcome and thanks for having us here. I'm Roberto and this is Michał. So we both work at WhatsApp. We are part of the developer infrastructure team. As you may know, a good portion of WhatsApp code base is implemented in Erlang, and that's why we can spend quite a bit of time around Erlang, trying to improve the language and trying to improve the tooling around the language. Today, we are going to present a project we've been working on for the past couple of years. It's called the Erlang Language Platform, or in short, ELP, not help. So before we dive into what the Erlang Language Platform is and how it works, we would like to spend a few minutes reflecting on something we use every day, tools. And we would like to focus on Erlang tools, low-level things like the compiler and the parser. And we would like to look at these tools through the lens of an IDE, which is probably what we are using every day to write our code. So when we think about tools like the compiler or the parser, generally speaking, these tools are they are part of the Erlang OTP distribution. When you download Erlang, you get these tools included in the package. You get the ErlC compiler, you get the parser, you get a scanner, you get a linter, you get dialyzer, you get edoc, and so on and so forth. Now, these tools are pretty good in what they do. They do a good job, but when you look at them from an IDE perspective, they have quite a few limitations. So the first thing is that most of these tools are not intended to be used in a highly interactive environment like the IDE. They are intended for as a batch tool. So the idea is you're writing some Erlang code in a text editor. Maybe you make a small mistake. You have a missing comma. Then you go to the terminal. You run ErlC. You compile. You get back an error saying, oh, you have a missing comma somewhere. Then you go back to the editor. You fix your error and you go back. And there is very little chance that you can use what you computed the previous time. You basically have to restart from scratch the entire computation. Now, it's unlikely that you do this kind of workflow. So you manually switch to the terminal and run ErlC manually. You probably have a more advanced build system that eventually call LC, something like rebar or buck or Erlang MK. But at the end of the day, ErlC is like what you invoke. These tools are also not resilient, meaning that there is very little error recovery in place. Imagine that you are typing some Erlang code, you are implementing the body of a function. And maybe you are trying to invoke a function which is defined in the same module. And you write like a case, an expression, you try to call the function, and then you don't recall what parameters I need to pass to that function. So I go there and I would expect to jump to the definition of that function. And if for a second you try and think what happens behind the scenes, you probably have some kind of tool that will parse the current module, find the function definition, find the location, and then when you jump to the definition, it will just go there. But since we are typing the current module, that module doesn't compile, doesn't parse correctly. So it's kind of tricky to know where that function is defined. These tools also are pretty bad in preserving some kind of metadata about the code or some extra information. Some of them lose positional information. For example, I think when you parse like a wild attribute in Erlang, some of the location of like where types are used or variables are used, they are like just lost in translation. Comments, white spaces are sometimes lost. And this is problematic from an IDE perspective, because if you think like, imagine that you're writing a tool that can allow you to select some text and refactor it to an external function. If you're losing the comments and the white spaces in the process, that's pretty bad, because when you extract the function, you really want to keep it as it is. That's also another problem by losing positional information, because if there is a problem with a part of the spec, you want to highlight the exact range where this happens. You don't want to highlight the entire line and say, there is a problem somewhere, just fix it. These tools are also generally not flexible when it comes to macros. So macros are hard, and the point I want to make is that depending on how you, like on the use case that you're working on, you may need different things from a macro. Imagine that you want to write a rename macro functionality in an IDE. You have a macro, you define a macro, and you use it in a bunch of places. What you don't really care about the content of the macro. So you want the like non-expanded version of the macro. Like I right-click on a macro name, I want to rename, I want all the other occurrences to be renamed as well. It doesn't matter what's inside the macro. But if I'm writing something like a type checker, I want the opposite. I don't care what the name is for the macro, but I want to infer as much information as possible from the types like inside. I want to see through the macro itself. Finally, a lot of these tools are not intended to be used as libraries. They don't really offer an API. An example is edoc. In Erlang, you can write documentation for your code. You can have this special syntax. It looks like Markdown, but not really. Hopefully, the OTP team will migrate to Markdown eventually. But let's say we have, like, you add these comments, and you can use this application edoc to extract them and to produce HTML pages out of it. Well, edoc does not have an API for returning the list of warnings and errors that you have in your comments. Maybe you mistype a quote. It's also like edoc generally puts all the errors and warnings in the standard output. So if you have writing a tool that interacts with edoc, you have to do all kind of evil stuff like playing with group leaders and process dictionaries and trying to extract this information and present it somewhere else. Now, these tools were not designed with an IDE in mind. They are good at what they do, and now we have another use case. So can we just go there and fix them? Well, as we said, these tools are mostly part of the Erlang OTP distribution. They come with the Erlang OTP repository, and the repository is quite strict when it comes to backward compatibility for good reasons. Like, you don't want to break all the software that we wrote because we want to change an API so that it's more convenient for an IDE. So we need a different approach. But we don't only have tools which belong to the OTP repository. We have other tools in the community. We have things like linters. We have Elvis. It's a nice project. It can detect bad smells in your code, but it has its limitation as well. Normally, Elvis, if you have used it, can detect things like duplicated code within a module. So if you're writing like a function and the implementation is very similar to another, it will prompt you. You can specify how many nested cases are allowed in your code. You can do like nice things, but generally it's limited. The analysis that Elvis performs is limited to a single module, so you cannot really do this analysis across the entire code base. And most important, Elvis aims at detecting these problems, not at fixing them. So if you have duplicated code in a module, Elvis will tell you this is duplicated, but it doesn't offer the functionality to fix that problem and maybe refactor it in an external tool. It's out of scope. On the other hand, we have other tools that can do exactly that. Projects like Wrangler or Refactor, they are like refactoring tools, so they allow you to do things like inline function, extract function, inline variable, and all sorts of things. But they usually come as a separate entity. You have to manually install them. Some of them are getting integrated with IDEs, which is great. But still, they have their own database, their own view of the code, their own understanding. So they do a lot of work that is already done by other tools. We mentioned tools and we mentioned IDEs. So how does an IDE uses these tools anyway? Most modern text editors use something which is called a language server. The idea is very simple. The architecture looks more or less like this. The IDE acts as a client. So it has a component which is called the language client, and that can be built in the editor. It could be VS Code or Emacs or Vim or whatever, or it can be an extension or a plugin for that text editor. And that client, that language client, is completely language agnostic. It doesn't matter if you're writing Erlang, Elixir, Rust, or whatever. That language client speaks a protocol. So the editor doesn't have to know about all details about the Erlang programming language or the Elixir programming languages. What's on the other side, on the server side, is a language server, which implements the language features that you would expect in an IDE. Things like code completion or go-to definition. And you can pick the technology that you prefer for the language server. It doesn't have to be the same as the language client. So if the client, the editor, is written eLisp, you don't have to write the language server in eLisp. Maybe it's more convenient to write it in Elixir if you're writing an Elixir language server. So in the Erlang community, there is a project that has been around for a couple of years. It got some traction, and it's a language server for Erlang. It's called Erlang LS, and essentially it's the glue between the IDE and the tools that we saw. But if we think well, that means that all the limitations that we experience in those tools are basically limitations in the language server itself. Because the language server is doing nothing else than calling those tools and formatting the result and speaking the protocol and returning these results to the client. Now, I think 15 minutes after the short introduction, now that we learn about the tools that we have in the Erlang community, the tools that we use, their limitations, we are ready to explain what ELP is. So ELP is a new project. It's code intelligence for Erlang. It means that it provides features that you would expect. So it understands your Erlang code and provides features, things like go-to definition, auto-completion, all the usual suspects. It's a database of live facts about your code. So live means that when you are in an editor and you're typing, it will basically keep a database up to date with whatever is changing in the IDE. It's a platform for building tools. So it's intended to be used as an API for other tools to integrate and use this database of facts to get creative and implement features. It's highly inspired by the Rust Analyzer project. For those who are not familiar with it, Rust Analyzer is the language server for the Rust programming language. As you might have imagined, it's highly focused on the IDE use case. So on things like highly interactive environment, incrementality, a lot of caching. It comes with a command line. So we don't want ELP to only be used from an IDE, but it can also be used as a tool from the command line so that you can integrate it with maybe your continuous integration and run your linters that way and so on with the same engine. And yes, it can act as a language server because once you have this database, writing a language server on top of this, it's a trivial thing. So effectively, it replaces everything that Erlang LS was doing until now.
Yeah, so let's talk a little bit about what a language server needs to be good at. And those are basically two things. One, it needs to do things in parallel, and two, it needs to handle deep trees. So let's explore those both aspects a little bit in depth. When it comes to parallelism, we frequently need to compute multiple things at the same time. So, for example, when you type a character and then edit in your editor, we need to update the source database that Roberto mentioned, recompute diagnostics, recompute code actions like launch test. For example, in the common test module, you want to have like a simple thing that allows you to start your tests from the IDE. We need to type check your code. We need to do many different actions, and ideally they should happen in parallel. At the same time, if you do go to definition and we're still computing diagnostics, we don't want to block the kind of returning results for go to definition just because we're still not done computing diagnostics. At the same time, we also have the use case where we suddenly have a big batch of job for the language server appearing, for example, during rebases, right? Where suddenly we might need to update tens, hundreds, or even thousands of modules at the same time. And if our engineers have servers that have 30 cores, we want to take advantage of all of them, right? We don't want to queue all of that just in a single process. At the same time, almost all the data structures that we need to deal with in a language server are highly structured, complex, and deep trees, right? Starting from the abstract syntax tree, going through different representations, going through types, everything is basically highly structured and complex. So all throughout this talk, we have had kind of a big secret, and that secret is this friendly little crab. So ELP is not written in Erlang. It is written in Rust. And I would like to kind of justify and explain this decision a little bit more. So talking a bit about those two things, high parallelism and deep and complex data structures, if you think about it, it's kind of a worst case scenario for Erlang. Because sending those complex data structures between multiple processes, which you need for high parallelism, is extremely slow, right? And just expensive. So if you want to avoid that, you're either limited to working in a single process, or you need to kind of somehow leverage ETS, which is our go-to solution for dealing with the problem. But then suddenly you're programming against a mutable storage, which kind of you lose all the nice benefits of functional programming. And then you need to either denormalize or flatten your data so you don't have those deep trees, and the whole thing becomes quite awkward. And as some sort of proof that our theory is correct for this, we did in our team some work on dialyzer, and we did see some edge cases where dialyzer can spend up to 90% of time copying data from ETS tables and garbage collecting, right? And it's basically similar in handling deep, complex trees and data structures and then many processes. You usually don't hit this in regular programs, but kind of compilers and type checkers is somewhat of a special case when you need something else. But we didn't set out to be yet another rewrite it in Rust project, right? Actually, early on, me and my colleague Alan, who's sitting a bit there in this third row, we set out to build two prototypes. One was in Rust, another one was in Haskell, to understand what are the limitations, what we can get from the tools. And what we quickly realized is that Rust has a rich and extensive ecosystem of libraries that we can leverage to get to build our tool. Right? In particular, the Rust language server, Rust Analyzer, that Roberto already mentioned, publishes many of its internal libraries as standalone projects that you can leverage, and that we do leverage to implement many of the features. Another tool that we did want to use is TreeSitter. It is a project to provide parser that can give you full fidelity, incrementality, and fault tolerance, so the properties that Roberto mentioned earlier. So what we mean by full fidelity is that the parse tree preserves all white space, all comments, all the formatting. You can transform from text to the parse tree, back to text, byte for byte. You don't lose anything. At the same time, with the TreeSitter, you always produce a parse tree. Right? No matter whether your code has syntax errors or not, you always get a parse tree. Part of that tree might be an error node that tells, like, this doesn't make sense, but the rest will be incorporated in some way, which is extremely powerful in the IDE use case, where, as Roberto said, I might say it a bit differently, you almost always work with broken code, right? The code while you're editing is almost always something's wrong with it. That's why you're editing it. But the second point is that this is a C library. So if we wanted to use it from Erlang, you would need to do nifs. It is quite an extensive library, so there will be a lot of nif code. And what's even worse is that a lot of the objects returned from here are not thread safe. Which means, and in the nif API for Erlang, we don't really have a way of guaranteeing that the object won't be shared between multiple processes, you won't accidentally send it to a different process, or even worse, that the process won't be just rescheduled on a different thread, right? And suddenly things can go very, very wrong. So one of the libraries that is used in Rust Analyzer and that we use in our tool is called Salsa. It's a general purpose engine for expressing your computation as a graph of pure functions. Right? In particular, it gives several very interesting properties when you can express your computation this way, because it gives us automatic memoization of the results, but not only that, tracking of dependency and versioning and recomputation. So for example, when you make a small change in your module, let's say we have something that needs the list of exported functions, right, to carry on another computation. And let's say you changed your modules, and then we recompute the list of exported function, but at this point, the engine will realize that, oh, the exported function is the same as it was in the previous time we computed that. So all the subsequent computation, we can just reuse the cached results. We don't need to recompute all of that, which is exactly what you want in an IDE, where with this granularity, you can avoid a lot of recomputation on changes, and you don't need to worry about caching and invalidating the caching and doing all of that, because this is handled for you by construction of how you write your program. Another aspect that we do leverage is the abstraction around file system. So file systems are just terrible. Right? One of the problems is detecting, like one of the least of the problems, but it's very annoying in an IDE, is detecting if two files are actually the same file. And this is surprisingly complicated because of symlinks. And then there are tools that love to use symlinks. I won't mention them by name, Rebar. But even with that, that's fine actually that you use that. It's a tool that you have. But we don't want to deal with all of that complexity while we're trying to parse and type check and detect errors in your code. So inside of the analysis, we basically work on an in-memory, some abstraction representation of the file system with everything read through, so we don't do any I/O during analysis. Another advantage is that when we're running as a language server, we can get file watching injected. So language server has a facility for just, you ask the editor to do file watching for you, which is much better than each language server doing this over and over again. When we're running in CLI mode, we leverage a really nice Facebook project called Watchman that allows you to do, again, file watching in a cross-platform way. So how is ELP structured? And it's very much the idea of this kind of layers. So at the very base, we have the concrete syntax tree, which we use tree-sitter for that. So it's untyped, it's full fidelity, as I mentioned, so we have everything preserved there. On top of that, we build an abstract syntax tree that is strongly typed, right? In particular, every node in your tree has a type, so when you're working with it, it's more natural. For example, like case will have clauses and things like that. Right? On top of that, we build what we call HIR. It's a nomenclature we inherited from Rust Analyzer. But the big idea there is that this is the layer where we do semantic analysis, right? So rather than doing a syntax tree of functions in a module, we'll have a list of functions with names that are defined in a module. And then those functions not necessarily have to have correct bodies, right, for us to compute a list of functions that is defined in a module. It's only at this point, and only at this point, that we do macro expansion. And I will talk a little bit more about macros later. And then finally, we have the layer that we call IDE, which exposes high-level concepts. Right? So for example, given this line, this column, what is the symbol and when it is defined, right? And this might be, I don't know, a variable that's defined 3 lines above, or a function that's defined like 10 files away, right? And then on top of that, we can build different use cases. And as Roberto mentioned, the main use case that we kind of were exploring was the language server and integrating to the editors like VS Code, Emacs, and others. But also we have this command line use case where whether this is interactive for engineers that don't like smart editors, or whether it's for CI. So if you have a lint that shows up in your editor and then you can fix it in your editor, we also can run it on CI, exactly the same one with exactly the same engine, and then automatically apply fixes on CI. And then, for example, you want to have a dashboard. If you have a type checker and you want to have a dashboard of how much of your code base is well typed, right? Again, you can leverage exactly the same information and exactly the same tool for all of that. So, macros. As Roberto mentioned, to do well what we set out to do, we need both a representation of code with macros expanded and not. For example, if you want to do type checking, you want your macros expanded. Or if you want to even go to definition, you want your macros expanded because you might have a record where the record name is hidden behind a macro. That's surprisingly common. But on the other side, if you do refactoring tools or code motion, you don't want your macros expanded, right? As we've seen, like you do extract a function and then suddenly everything's expanded. It's not really what you want. So with our architecture, we can, and then different layers of abstractions, we have macros both expanded and not expanded, but we can move fluently between those representations. So you can very easily, for example, compute position using the expanded macro format. But then when we need to apply refactoring, we move back to the format with the macros not expanded and can apply the transformation. Unfortunately, in this mode, parse transforms are more or less impossible to support. We're fortunate that internally we don't use them. But in general, they are highly problematic because they are non-local. They operate on the entire module. So with all of the work we did with incrementality, we suddenly cannot limit the impact that a parse transform might have. You can do arbitrary things. And then the API parse transforms have for interacting with the compiler is fairly limited. It's just the Erlang AST, which kind of limits what abstractions you can introduce and to some extent limits the compiler as well, because it's very hard to evolve the AST if any change might break any parse transforms that are in the community. So it means we do handle macros very differently than Erlang compiler does. Right? Erlang compiler expands macros very early, just after tokenizing, it processes macros, yet still before parsing. We do it differently. We parse, kind of, to some extent, pretend that macros are sort of functions and expand them that way. It means, however, we cannot support all the macros. In particular, we cannot support macro where you have opening bracket in one but closing in another one. It is a valid Erlang program. Fortunately, and I think good for our collective sanity, it's not common to have programs like that. So this limitation is not a major one in practice. But sometimes we do need to actually call Erlang code. And for that, we have a small, what we call Erlang service. It's a eScript that runs as a sidecar to the main language server. And we use it for things like edoc, or where we do need to evaluate Erlang code. And we need that, for example, for integration with common test. So to understand what tests are defined in the module, we need to call the all and groups function and evaluate them. And a bit on a technical side or implementation side, but I think it's quite interesting. So I wanted to talk about is how we test this whole thing. And we mostly use snapshot testing. So for example, we in here on the left side, or it's right side for you? I know, this one. We have one of the tests we have for go to definition. So the tilde sign will mark where the cursor is, and then the underlines will be where it was resolved to. And then on the other side, we have a test for diagnostic, right? So again, we see that if we type check if we check the code, we'll have a diagnostic reported, and again we see where it is reported with the light bulb, meaning there's an automated fix for it, right? And then at the bottom we have a test that checks what happens when we apply the fix. And the good thing about all of that is that those are self-updating, right? So if you change the code to do something else, you can just rerun your test suite with some flag, and all the tests will be updated to reflect the change, which is extremely useful if you're just developing or updating or fixing bugs and stuff like that. It speeds up things tremendously if you don't need to go and fiddle with the text all the time. There is a downside of not having it in Erlang, and this is we cannot really use our tool while working on it. So with Erlang LS, if you are working on Erlang LS, you are using Erlang LS, so you could see some problems and small inconveniences. Here we need to rely much more on our users to report those. On the other hand, we can get inspired on some of the features and things that the language server can do for you. And I think Roberto will tell us more about those.
Right, so we saw what ELP is, we see roughly how it works, how it's structured, but okay, what can ELP do for me right now? So ELP has basically everything that you would expect from a language server, but with like a bit of extra powers. So there is like a full feature gallery of things that are available. Let's take one as an example, diagnostics. Diagnostics is the ability to see like warnings and errors in your code, in your IDE. Well, because of how we compute things, compared to like Erlang LS, these diagnostics can be basically enabled as you type, if you like that, instead of when you save, because they are like that fast. Most importantly, often in Erlang, when you have a small mistake in your code, like a missing comma, you get a cascading flow of errors, like undefined functions. Oh, this is not exported, this is undefined, this is unused, and so on. What we can do is that we can actually aggregate related diagnostics, so you can actually see, oh, there is a missing comma, and out of that, like everything else happens. And most importantly, we can also auto-fix most of these problems, so that whenever you have a problem, like this variable is unused, or this function is unused, you could basically click on the bulb and do like export or delete it and so on. And you can do these things through the IDE or by the CLI. It comes with built-in refactoring, so all the usual suspects, things like inline function, inline variable, extract, expand macro, and so on, they're all available. Now, due to timing constraints, we cannot really show like a live demo of how it works, but one feature we would like to show, because we think it shows it condenses like the essence of ELP. This was contributed by one of our colleagues. Video cannot be loaded, so great. It's a great feature. So
should we try to fix it?
No, I think we can. Maybe we can show it. Like I can explain what it is at least, but video cannot be loaded. But it's types on hover. So essentially, your IDE, there should be like an IDE there with some code and some variables, and with a cursor you can hover a variable, and you can actually see the type of that variable as it flows through the code. ELP is tightly integrated with the equalizer, the type checker, so we can basically use that information for telling you what the type is. So when you're chasing a bug and seeing like, oh, what is this problem, you can actually see, oh, this is a binary or undefined. Oh, you can track it to like what it is, and you can also like jump to the type definition. We'll see if we can show it. Let's see. So what's the current status? We consider ELP like stable. It's been running at WhatsApp for basically a year. it's effectively like being substituting like Erlang LS. One of the conditions was to replace every single feature so that developers would not lose anything. So now ELP offers a superset of Erlang LS. It's open source, it's on GitHub. We have packages for Mac and Linux. It's integrated with build systems, so you have a Reaper integration, you have a Buck integration, and Roman, our colleague somewhere, is working on a way to write a project manifest, some kind of like JSON or some other format, where you can, if you're not using one of the supported build systems, you can basically tell where your dependencies are, where your includes are, and so on. We have plugins for Emacs through LSP mode and Iglot. We have a VS Code extension, which is still kind of needs some love because we internally use like a separate extension, which has a lot more. So we still need to port some of the features. So on the server side, everything is ready. On the client side, might need some love, but that's where we are. And also, like someone from this audience, I think yesterday submitted a pull request for adding NeoVim support. It's on GitHub under WhatsApp, Erlang Language Platform, and I think that's it. We have logo, which means also we have stickers if you need. And we have equalizer stickers as well. Should we try and fix that?
And the stickers are shiny.
Yes. Should we try and fix the video?
Let's try the video. Where's my mouse?
Maybe in the meantime we can
take questions.
Yeah, someone have a question? Run over there. Oh my gosh.
That's not a good.
It's a
So, question. Could you plug in dialyzer in this? I mean, of course you could, but could you do it in a reasonable way?
You could, if you have a lot of time. Are we?
Yes, we have a video. So I didn't lie. So you can actually see the variables, and you can see like what the types are, and you can jump to definition. And in the video, there was also like another, kind of like another feature, which is somehow hidden here, which is this inlay hints. So through LSP, you can basically like annotate your code. So this is virtual text in your editor, and whenever like you're calling a function and the parameter names do not match, we can show you what it is. So for example, like line 337, someone is calling a variable that is called server ref, but is passing service ref. Maybe that's intended, maybe that's unnecessary. Or you can see that the gen server call actually has a request and a timeout, so you actually see the meaning of those.
Cool. I think that's all the time we have for now. So find them afterwards and ask on Huva. Thank you very much.